Hello, my name is Monique Morton. I am the Senior Content Director for Mathematics and Computer Science with Advanced Kentucky. This video is a review of optimization problems for AP Calculus, and I'm going to work through the steps of the problems, including the justifications. So our first step is always to read the problem, so let's read our first example. A rectangle is formed with width x and height y, such that the point xy is on the graph of y equals 4 minus x squared. What is the maximum area of such a rectangle? So we've been provided with the diagram. If we weren't provided with one, I'd probably draw one, where here is my width x and here is my height y, and this is the curve y equals 4 minus x squared. Let's start with writing an expression for what we want to optimize. In this case, we want to find the maximum area. So I need an area equation. So it's a rectangle, so area is going to be x times y. Now, what I want to do is I don't really want this in terms of x and y. I want to express this optimization equation in terms of one variable only, make it a function of just, let's say, x. So I go here and I notice that y is equal to 4 minus x squared. I have a constraint on y. So I can rewrite my area expression as a function a of x is equal to x times 4 minus x squared, or better yet, 4x minus x to the third power. So that is my area function. Now, since I want to maximize the area, I'm going to look for critical points, find the critical points, do an analysis on them using first derivative test, second derivative test, or the candidates test to be able to answer my question. So in order to find critical points, I need a derivative. Since a of x is equal to 4 times x minus x cubed, x prime of x, a prime of x, sounds like I said x prime, sorry about that, is equal to 4 minus 3x squared. Now this might be a good time to note that x can't be any value, right? The domain of this function, this area function, is not all real numbers. Because if you imagine us moving this point xy up and down this curve, the further I can go where it would make sense would be up here on the y-axis, so x has to be bigger than 0. And the farthest I can go before it starts not being a rectangle is down here to 2. So it's a good thing to note that x has to be contained between the values of 0 and 2. That also means that I'm only going to be looking for critical points that are between 0 and 2. So to find the critical points, I need to set the derivative a prime of x equal to 0, or look for where it's undefined. In this case, it's a polynomial, so it's never undefined. So I just need to solve for when the derivative is equal to 0. This is when x squared is equal to 4 thirds, which means that the absolute value of x is equal to 2 over the square root of 3. So x is either negative 2 over the square root of 3 or positive 2 over the square root of 3. Now, since we want values between 0 and 2, I'm going to ignore this negative option, right, because it's not on the realistic domain of my function. So the only critical point I'm going to be concerned about here is 2 over the square root of 3. Doing a quick sign analysis of the first derivative, really just being concerned about what happens from 0 to 2. And 2 divided by the square root of 3 is going to be between them. It's going to be a positive number, and it's going to be smaller than 2. I believe that means that between 0 and 2 square root of 2, looking back here, between 0 and 2 over the square root of 3, my derivative is going to be positive. And between 2 over the square root of 3 and 2, my derivative is going to be negative. Now, actually, I'm thinking in my head of what the graph of this looks like. It's a parabola similar to this one that opens downward. So that's how I thought of my signs. Some people like to use test values, and that's okay. So since the sign of A prime changes from positive to negative, I know that that means that this is a relative maximum. And furthermore, since it's the only critical point on the interval, it's an absolute maximum. So I'm going to say this, that A prime of x is positive for values of x between 0 and 2 divided by the square root of 3. And A prime of x is negative for values of x between 2 divided by the square root of 3 and 2. So therefore, the area is maximized at x equals 2 divided by the square root of 3. Now go back up. They want the actual area. I haven't actually found that. I just found out where it occurs. Okay. So the actual area, A of 2 divided by the square root of 3, would be equal to, there's my area function, 2 divided by the square root of 3 times 4 minus 2 divided by the square root of 3 squared, or 2 divided by the square root of 3 times 4 minus 4 over 3. 12 minus 4 is 8. That's 2 divided by the square root of 3 times 8 thirds, which is 16 divided by 3 root 3. Okay. That's the answer to the question. So this is a good problem to really think about the steps in solving this type of problem. Step 1 is always to read the question all the way through, making sure that you understand what you have and what you're being asked for. My next thing is really realizing what I'm maximizing. Right? This is my optimization equation. Now, before I do that, I might want to draw a diagram. When it's possible and appropriate to draw a diagram, I suggest always doing it. A labeled diagram will make it a lot easier to come up with your optimization equation and your optimization function. Okay. Make sure that you find the critical points. And you do some analysis on the critical points and talk about where they're positive or negative. Eliminate anything that's not in the domain. Here's my domain. Eliminate any values that are not in your domain. Here, I actually used the first derivative test to justify my extreme value. And by writing it with these intervals, I've looked at the numbers over the entire domain. So I know that I'm talking about an absolute maximum and not a relative one. And then I need to answer the question. So these steps are all general steps in solving optimization problems of any type. And let's look at a different type of optimization problem. This one is a particle motion problem. Reading. A particle moves along the x-axis such that its position at any time t, where t is between 0 and 5, is given by the function x of t equals 3 times t minus 3 to the 2/3 power. That really should be an exponent. I hope you notice that it's not really on that bottom line. Times 2t minus 1. At what time t, where t is on its interval, is the particle farthest to the left? Well, since we're moving back and forth along the x-axis, to the left are smaller x values, and to the right are bigger x values. So what we really mean by farthest to the left is we want the minimum value of x. So this is my x equation. This happens to be my optimization function. They gave it to me. So in order to optimize this, I'm going to need to find the first derivative so I can find the critical points. So x prime of t is equal to, I'm going to use the product rule. 2/3 times 3 is 2 times t minus 3 to the minus 1/3 times 2t minus 1 plus 3 times t minus 3 to the 2/3 power times the derivative of 2t minus 1, which is 2. So I think that I am going to factor out a 2 and a t minus 3 to the minus 1/3 power. So that'll leave me with 2t minus 1 in the first term and plus 3 times t plus 3, oops, not plus, minus 3 in the second term. Right? Because if I multiply this together, that would give me 1, and I started out with the 1/3 power. This is 2 times t minus 3 to the negative 1/3. Just doing a little simplifying because I'm going to need to use the numbers. 2t plus 3t is 5t. And minus 1 minus 9 is minus 10. Oh, and I'm going to factor out a 5. So I'm going to write this as 10 times t minus 2 divided by t minus 3 to the 1/3 power. That's my derivative. So, critical numbers. Critical numbers are values where the derivative are equal to 0 or undefined. Now I can kind of just look at this and notice that this derivative is equal to 0 when t is equal to 2. But it is undefined, the denominator is equal to 0, which makes the fraction undefined, when t is equal to 3. And notice that both of these critical points are actually on the closed interval. So what we're going to do here is we have a closed interval from 0 to 5, and we want to find the absolute maximum. This will be a good point to use the candidates test. Right? I have actually 4 candidates, t, x of t. Right? I have the endpoints, 0 and 5, and I have the 2 interior critical points, 2 and 3. So I'm going to put these values into the function as best I can. So when 0 goes in here, I get 3 times negative 3 to the 2/3 power times negative 1. Right? And I don't know what that number is, but it's negative. Well, I'll make an effort to try to find it. Let's see, if I square this, this is 9. So this is going to be negative 3 times 9 to the 1/3 power. I think that's good enough. When I put 2 in to x of t, I get 3 times 2 minus 3, which would be negative 1 to the 2/3, times 4 minus 1, which is 3. So this is actually 9. When I put 3 in here, I get 3 times 0, dot, dot, dot. This is going to come out to be 0. And when I put 5 back in here, I get 3 times 2 to the 2/3 power times 10 minus 1, so that's 27 times 4 to the 1/3. And I'm looking for when it's farthest to the left, and so that actually happens, let me go back and check my arithmetic again, yeah, that actually happens here at this endpoint. Right? That's the smallest of the 4 values. Right? So therefore, the particle is farthest left when t is equal to 0. So we read the problem like we did before. We already had our position function, so we didn't need to actually set up an optimization equation. But in order to find that minimum value of x, we needed to find the derivative, find the critical points. Notice that there were two. One that results when x prime of t is equal to 0, and the other that results when x prime of t is undefined. And I chose to use the candidates test since I had two interior critical points to determine which of these values would be the smallest, i.e., when would the particle be farthest to the left. A sheet of metal 12 feet by 15 feet will be made into a box by cutting equal-sized squares from each corner and folding up the four edges. What would be the dimensions of the box with the largest volume? So after reading this question, I realized that it probably will help me to draw a diagram. So I'm going to start with just that. So I have a sheet of metal that's 12 feet by 15 feet. Now I'm going to cut out equal-sized squares from each corner. So there'll be a square in this corner, and in this corner, and this corner, and this third corner. They don't look much like squares with my drawing, but let's assume they are. And I don't know how long these squares are going to be, so I'm going to label them with variable. And since they're squares, all of the sides are going to be the same length. So let's call this variable x. Now, what I want to maximize here is volume. Let's take a moment and think about what this box is going to look like. So when I cut these squares out, right, these are not going to be part of the picture anymore. I'm going to fold these along these lines. And I'm going to end up with a box that's open on the top that looks something like that. Let's say that this is the length, width, and height of the box. The volume of this box, because I want to find largest volume, would be found by multiplying length times width times height. So we need expressions for length, width, and height. Well, the height is going to be one side of this square, isn't it? Because when I fold this up, this is going to go up vertical. So h is going to be x. And if I think of this side over here on the right as the length, you know, from here to there, this whole length is 12 feet. But I'm going to cut off these squares. So I'm going to cut off x on this end and x on that end. So the width is actually going to be 12 minus 2x, right? Because I'm cutting off 2x's representing the two squares on each end of the side. And I'm going to do the same thing over here, the 15-foot side. That's going to be equal to 15 minus 2x. So the volume, v of x, is equal to 15 minus 2x, that's not a 15, 15 minus 2x times 12 minus 2x times x. That is my volume expression. So when I go back and look and multiply this all out, I've already done it over here to the side. So my volume expression is going to be v of x is equal to 4x cubed minus 54x squared plus 180x. That's the equation that I want to maximize. This might be a good point to stop and think about domain. So x clearly has to be bigger than 0, right? But how big can it be? Well, this side's longer than this side, so this is going to restrict it more. And it can't go past the halfway mark, can it? Because then the x is overlapping parts that I already cut off, and that doesn't make sense. So I'm going to say that the domain is restricting x to be between 0 and 6. That makes sense? Okay. So my next step is going to be to find the critical points so that I can maximize the volume. I'm only going to be worried about critical points that are on the interval from 0 to 6. So v prime of x is equal to 12x squared minus 108x plus 180. That's v prime of x. And remember that x is going to be between 0 and 6. Now, I've worked this out ahead of time, so I already know this doesn't factor. So I'm going to go ahead and go to a graph of the derivative function. So here's the graph of the derivative function. The derivative is 12x squared minus 108x plus 180. Carrying this out to the appropriate number of decimal places. The actual, excuse me for taking so long, but this value out to 3 decimal places, okay, I'm going to write 4, is 2.20871. There's only one critical point between 0 and 6, and it's this number, which you can see rounds to 2.21, but you should get into practice of expressing things to at least 3 decimal places in your classwork for AP Calculus. So I'm just going to use this graph since I see it. V prime of x is positive for 0 to 2.209. I'm going to round it to 3 decimal places instead of 2. And v prime of x is negative for 2.209 until I get to 6. That's only one critical point on this entire restricted domain. The maximum volume occurs when x is equal to 2.209. So let's go back to the question. The question asks what are the dimensions of the box, and I'm going to see if I can get both of these things to show up at the same time. Here's my volume equation. Well, actually, all I need is the picture, right? Length, width, and height. So the dimensions of the box are 15 minus 2 times 2.209 and 12 minus 2 times 2.209 feet and 2.209. You can get it together and simplify that expression if you want, but writing it this way allows you to see where the numbers are coming from. So this one was a little bit more difficult in terms of finding the critical points because it wasn't an easy thing to, it was a quadratic. We could use the quadratic formula, but I decided to graph it and use my graphing calculator to find the critical point. And since I had the graph looking at myself, you went ahead and used it to do the first derivative test. So I have one more example to do after this sheet metal, and this is my last one. A rectangular garden plot is to be built along one side of an apartment building. The garden plot will be divided into 4 side-by-side plots of equal size with parallel partitions perpendicular to the building. What is the maximum area of one of the subplots if there is 140 feet of fencing available to build a garden? So let's say this line here is the side of the building. And I just went straight into drawing a diagram because I need to picture this anyway. Okay. So we're going to build a rectangular garden. So here's my garden. And it's going to be divided into 4 side-by-side plots. So here are my plots. I have 140 feet of fencing, believe me, but I need to maximize area. So if I want to maximize the area of one of the subplots, let's label one side Y and the other side X. Right? I want to maximize the area of one of the subplots. So, in fact, all of these subplots will have the same width, since we said we wanted them to be equal. And all of these partitions will have the same length, because we want these to be equal. And I know that I want to have my area equation, my optimization function, if you will, in terms of X alone. So let's see if we have any constraints. Yeah, we only have 140 feet of fencing. So that means if I add up all of these lengths and add up all of these lengths, it should add up to 140. So I have 4 X's and 5 Y's, and they need to add up to 140. So here's my constraint. I'm going to use my constraint to help me to get an area function in terms of just one variable. So I'm going to go ahead and solve this for y. 5y is equal to 140 minus 4x. So y is equal to, let's see, that's 28 minus 4/5 x. So my optimization function, my function in terms of one variable alone, is x times y, which is equal to 28 minus 4/5 x. That's the function I want to find the maximum value of. So finding a maximum, need critical points. If I need critical points, I need to find the derivative. So I'm going to go ahead and first multiply through by x, because I think that's going to make it a little easier to find the derivative. And find a prime of x. A prime of x is going to equal 28 minus 8/5 x. Now this expression can be equal to 0 when 28 minus 8/5 x is equal to 0. It's never undefined since it's a polynomial. So 28 equals 8/5 x. 5/8 times 28 is equal to x. So 2, 7. X is equal to 35 over 2. Okay, so that's my only critical point. I do have restrictions on x and y. I don't really know what they are, except that this has to be true. So I could probably say that x has to be positive and less than 140. That will take care of the biggest part. I'm going to go ahead and use the first derivative test. Right? This function is linear, so it only has one critical point. So there's only one critical point. This might be a good time to try out doing a second derivative test. What do you think? So here's my value. This is a prime of x is equal to 0 at 35 halves. It's pretty easy to take the second derivative. A double prime of x is equal to negative 8/5. And since this is negative, right, that's less than 0, that means that there must be a maximum at x equals 35. So, since a prime of 35 rather over 2 is less than 0, and a double prime of 35 divided by 2, or actually this is equal to 0, right? That's really important. And this must be less than 0. And x equals 35 over 2 is the only critical point. Me saying that this is the only critical point is emphasizing that I'm considering the entire possible domain. The domain is limited that x must be greater than 0 and probably less than 140. But even if I don't consider that, there's only one critical point at all, and it's this one. So there's only one sign change. This is it. So by the second derivative test, the maximum area occurs when x is equal to 35 halves. Right, so there's my justification using the second derivative test. I hadn't done that anywhere in this particular video. And I look at it, it's like, what is the maximum area is what they're asking for. The maximum area of one of the subplots. So since x is 35 halves, y must be 28 minus 4/5 times 35 halves. So 28 minus 14 times 7 to 28. So it's 14. So the area max area is 35 halves times 14, which is 7 times 35, which is 245 square feet. That's going to be my last example. I hope you found these examples helpful in your review of optimization problems. I try to include a variety of problems, including ones where diagrams are given, where you had to draw diagrams in a context. They all have a context in it, but all of the steps are similar. Read the problem, make sure you understand it. You need an optimization equation. You should look to see if there are any constraints. It's a good idea to think about domain. You really think about domain before you get too far into analyzing the derivative. And you can do it doing the first, second derivative test. The candidates test is another possibility for justifying the max or min. And make sure you answer the question. Right? There are a number of students who would have stopped here, but that's not what they asked. They asked for the actual maximum area. Anyway, hope you found this helpful. Goodbye. Good luck.